Ted Dunning.
Okay. So a quick question to the AV guys. Does this work?
Yes.
Great. Because I like to jump around and wave my hands a lot. Okay. What I want, volume control there, physics. I'd like to talk about some recent work that we've been doing in the Mahout project for very, very fast clustering, single pass k-means clustering. And before I get going on that, I'm Chief Application Architect at MapR. There's a hat, in case anybody forgets. We're hiring too. I'm a committer and a member of the Apache Software Foundation. I work primarily on Mahout, Zookeeper, and the recent Apache Drill project. I have worked a lot on Hadoop and a bit on Lucene over time. And I've been involved in, it's okay to say that in this audience, in open source for a long time, since long before the internet. First open source project I was involved in was 1975. So we're hiring is the key takeaway here. You can contact me any number of ways. What I'm going to talk about tonight is not MapR. It's open source stuff of math and software. And so we're going to first talk about the rationale for this style of clustering. I'm going to talk about some of the theory behind it and why clustering has been such a hard problem in the past and why this approach changes that. And then a couple notes about the algorithms that we use here and why they are very, very fast. Then I'll go into a bit about how we implemented it in the Mahout project and some of the results. So the basic idea here is that clustering is not so much a replication of how people would categorize data, but it's a very, very useful tool internally. It's a tool for data compression. It's a tool for search. You can use k-means clustering or other clusterings to make very fast nearest neighbor models. And it's a tool for characterizing probability distributions. And if you have a good clustering, you can do things like search that runs really, really, really fast against a huge number of data points. You can also build models. You can do data mining, classic supervised learning, using these unsupervised values as features for the supervised learning algorithms. And you can often, well, not often, we could say often. In my experience, I have often found that these cluster-based features can give you very, very good model performance, where conventional features had an extreme difficulty. At least conventional features applied to the learning algorithm that we were using. And it's because it discovers low dimensional manifolds in the distribution of your data. Now, to do all this, you have to have good clustering. And so the key question there is, what does good mean? A lot of people think that a good clustering would be one that if I inspected the clustering, I would say, yes, by my received wisdom, this is good. That I could recognize good clustering if I saw it. But in fact, this utilitarian view of clustering that I have, that it's good for compression, or that it's good for classification, or that it's good for other kinds of learning, that really means that good is as good does. And so if the clustering behaves on held out data well, if it describes the data compactly, when you give it novel data, then it is good. That is pure and simple enough to say that it's good for this utilitarian sort of purpose. And I contend that for these sort of utilitarian things, that agreement to some gold standard of a priori clustering is not necessarily an important criterion. And it's not even a very important criterion that the clustering is robust, meaning that it gives basically the same clustering every time you run it. As long as it gives you a clustering which, on held out data, gives you a good description, it's good. Here's an example. This is a classic sort of thing that people say, oh, symmetrical clusters isn't going to do well on this kind of data. They're a classic counterexample for k-means clustering. They are, in fact, however, if you look at it, a very low dimensional manifold. It's a line with noise on it. Now, it happens to not be a straight line, which makes describing the data a little bit harder. And it does have noise on it, which also makes it a little bit harder. But clustering this can still work because we can take that data and cluster it as so. Now, we have many clusters here, but every data point is going to be close to a single cluster. So if we just used which cluster it was nearest, I'm going to give these guys a small privilege here. If we just knew that it was next to this cluster, we would know within this much error, which is the size of the noise anyway, where that data point is. And likewise, if it was at the next cluster over, just point to any data point up there, any X. If I just said that a data point is near there, I know within a ball about this size, I must not stand on the speakers, a ball about that size on that screen where the data point is. And so this already will compress that data, and you can have pretty high assurance if the new data is from that spiral, it will have the same probabilistic characteristics as the old data. So with an error that big, we can compress the position of any of those data points down to 4 and a little bit of data bits per point. And we can decrease the area, or the error, by increasing the number of clusters, and we can decrease the error by actually retaining the distance to the nearest few clusters. And so that is a good clustering in that it describes the new data that we would see from that spiral well. And here's a picture of how well we can sort of see that. All across the bottom is the sample number, vertically is the cluster ID, and you can see that pretty much every data point, just walk up from there, it is near one cluster. It is not near very many clusters, so we just have the distance to the nearest 2 clusters and which side it's on. We could compress the position within that spiral very well. And even if the data was such that we look at it and we say, oh look, by color and position, we can assign a clustering to this data. We see bumpy data in this sort of way. Even if we were to cluster it with all of these clusters there, that's okay. That's really not so bad. That's a fine description of this data, because these overly ornate clusters that we have there show the shape of the data, even so. And so if we were to add way too many of those data clusters, if we were to get down to where every one of these data points had a cluster sitting on it, then we would have too many. Because then the behavior on the training data and the behavior on the held out data would be very different. Every cluster would be sitting on a data point in the training data, and in the new data, everything would be shifted. And so we would see a much worse than expected quality on the held out data. So that's my take on what clustering should be, is it should describe the data distribution that we are given as training data. So, here's a little bit of theory. And so traditionally, the way that clustering like this is done is we try to find cluster centroids which absolutely minimize, say, the squared distance, or the sum of the squared distance to all of the data points, from all the data points to the nearest cluster to each data point. And as stated, over all possible distributions of data, that's a nearly impossible problem to solve in a reasonable amount of time. It's incomplete. It's just not feasible. And one of the big changes in the last 10 years is that researchers have said, we don't care about any kind of data. We care about plausible data. And in the simplest case, we care about easily clusterable data. And that's data for which the correct clustering with K clusters is considerably better than the best clustering for K minus 1. It means there's a distinctly better clustering at a certain number of clusters than for any smaller number. And data that has that property is data that looks kind of like this on the next slide. Data that's in nice little tight bunches. And the way that they describe this is they talk about the K-summed squared distance. I would go to talk to you guys too, but I'd be afraid to pass the dreaded speaker. And so here we say that sigma squared is, for the K minus 1 clustering that's best, is bigger than the K clustering by that factor, at least that factor. And we can show that an interesting approximation algorithm exists, which gives us a clustering that is within a bound of the best. So these are always exciting algorithms where we can come within a, great idea. Signal to noise and a clustering bound and that sort of thing here and here. Sigma squared is 9 or something like that because it's square distance. Yes, see, those bounds are exciting. I'm free. So this is the picture here. If we took a 5 clustering of this data, then the error is going to be this big. Fingers close together sort of big. If we take a 4 clustering of that, those 2 clusters down in the lower right have to go together to find the best 4 clustering, and the error goes ba-cum, and it's now this big instead of that big. So this is well clusterable data because it has that property, and because if you just look at it, you can tell that it's easily clusterable. And so it's this kind of data that they're now proving these bounds on. Now, if we look at certain algorithms, Lloyd's algorithm is the one that everybody knows about. It started in the 50s, wasn't published until the 80s because everybody knew. It was just kind of folklore. And in fact, this is the algorithm that most people call the k-means algorithm. But in fact, it's not the k-means algorithm. There's dozens or hundreds of them. This is just the one that everybody knows, and that is start with k starting points, new centroids for the data, and repeatedly assign each data point to the closest. And then find the new centroids, and yada, yada, yada. Off you go. Now, it gives you radically variable quality, sometimes wonderful, sometimes horrible. Even on very highly clusterable data, it does things like this. This is the results of a real k-means thing. And so it says, oh, there's 5 clusters. Good, doing good. But it says the 2 blue clusters are 1 cluster, and it says the red and the green up in the upper left are 2 clusters. Now, this is stupid. This is bad. And the reason that it wound up this way is because it had 2 initial starting points in the upper left cluster, and it had 1 starting point in one of the 2 blue clusters, and then it had a starting point in somewhere near the green and the purple cluster. And k-means, as it stands, cannot recover from that. K-means-like algorithms, which are greedy hill climbing algorithms, cannot recover from bad starting positions. And so there's a whole class of algorithms, basically around this one, vol k-means or k-means plus plus, which crucially depend on getting better starting conditions. And that's enough to give provably tight bounds on convergence on this well-clusterable data. And in practice, gives you very good clusterings for practical data. And all that happens is instead of starting with random starting points, we start with starting points that come from a joint distribution that maximizes their distance apart in the original data distribution. Now, for two means clustering, it's great, it's awesome, and it's provably very high probability of being near optimal. Unfortunately, the probability that it's really good drops exponentially in K. That sounds horrible. And then there's this complex re-estimation of the seeding that can be used to get a higher probability bound of the correct sort of solution. But that takes a long time. It has K cubed sort of expense. K is the number of clusters. And if we're looking for 1,000 or 10,000 clusters, K cubed is just off the table. And it also has N times K times D complexity even so. So if you have 1,000 clusters, you have to go through the data several times. And that's also just not good enough. Not good enough for big data. It's fine for little data. If you only had 1,000 data points or 20,000 data points, it's really not so bad. And if you're only looking for a modest number of clusters. If we look back, the problem here is that we only picked 5 starting points. If we had picked 20 starting points, we would be just almost a dead cinch to find at least one starting point in each actual cluster. And then we could just kind of cruise through it, and we would have a good answer. So, that leads to this class of algorithms that I'm talking about tonight. That was an introduction. But now we get to the exciting stuff. And the idea is that we start with a very sloppy single pass clustering with a lot of centroids. How many centroids? If we want K at the end, K times log n, where n is the number of data points we've seen. That is a good enough surrogate then. We use that surrogate, those many clusters. We use those as a replacement for our data. They stand in for the data. They have a weight, which is the number of data points that's been assigned to each one of those sloppy surrogate clusters. And that weight and that position provides us with a kind of a weighted sampling of the original data. And there's a wonderful theorem, which I can't just do offhand, which says that this weighted surrogate with a ball k-means clustering will give us a good clustering of the original data. We only really cluster the surrogate, and we have a fast way to get the surrogate, and the surrogate is small. And so we have a fast way of getting the overall clustering because the surrogate is tiny. Yeah?
So it's only dependent on K and N, not the number of fields. Are you ever considering like having 10,000 fields?
Well, implicit here is the dimensionality of the data. That affects the cost of every operation, every comparison. So yeah, the dimensionality is still there. Now, amazingly enough, the sloppy clustering doesn't much care about that, the dimensionality.
There's not much of a recursive dimensionality issue?
No, because it uses a projection into a very low dimensional space as an approximate nearest neighbor search. And we'll get into that when we get into the actual implementation. But that's a really clever trick that they do there, which makes it almost dimensionality independent for the single pass. I mean, you still have to read the data, so you have some dimensionality dependence right off the bat. You still have to project it once onto this low dimensional projection. But from then on, you're done. And so there is, of course, an n times d in there, but it's not a k times n times d. Yeah?
Can you preserve the dimension but sample each dimension to start off with to reduce the n squared?
You could project the data originally into a lower dimensional space and then cluster in that lower dimensional space. And there's a theorem, Johnson-Lindenstrauss theorem, that says that there exists a projection to a lower dimensional space which preserves approximately the distance that you originally had.
I just know some people, they don't want to use like PCA or they need their dimension. They can't throw away, they can't reduce their dimension.
They can or cannot.
Cannot.
Yes, some people cannot, although everybody can to within some accuracy bound. That's what Johnson-Lindenstrauss says. is that if you are using Euclidean metric, you can reduce the dimension. And you can't necessarily reduce it to 3 dimensions, but you almost certainly can reduce it to, say, 1,000 dimensions. And if that's low for you, you win. If that's big, then, sorry, no hope for you. But this doesn't depend so much on the original dimension, these results. Let's go through it. Anyway, so the Lloyd's algorithm calls order of k times d per data point. You have to look at all of the cluster centroids you have. It costs about d to do each comparison, and you have to make several passes, which is probably at least log of n, or log of nk, or something even bigger through the data. So that's roughly what it costs per data point to do k-means. And the surrogate thing does a fast, sloppy clustering to k log n clusters. And we do a fast, sloppy search within those clusters. And the sloppy search costs us about log of kappa, because it's not an exact search. And so the overall cost now is log k instead of order k, and log n instead of k times d. And we then have the fast in-memory search, which can cost k cubed, or if we're willing to have a larger k, we can cut that to something like kappa d log k. And the result is very high quality centroids. Better than, in many cases, if we had tried to do some sort of clustering on all the data, because the cost of clustering on all the data is so high. So how much faster are we talking? If we have 2,000 clusters that we're trying to get, 10-dimensional data, which is low or high, depending on which one the customer, in this case, wanted 10 dimensions, and 100,000 data points, then we can do the math, and we come up with 500,000 for one alternative, or 170 sort of units, magic units of time for the other, about 3,000 times faster, neglecting I/O and things like that. So the constants on those various terms may make one dominate over another, and could make just reading the data be a nearly dominant form. But the algorithm itself has these very large accelerations available. And the accelerations are bigger if we have higher dimensions or more data. So this is a big deal. Now, here's some problems. We still have to have a very fast search internally. We have to cluster on the fly. We have to have an algorithm for doing one-pass online clustering for the sketch, for the surrogate, and we have to guarantee the sketch quality or something. Previously on the West Wing, these algorithms had very high complexity, and they existed, they were theoretically interesting, but their constants were so high that they just weren't useful. But the paper that I'm quoting from here, Meyerson, Schindler, and Wang, showed that a very sloppy clustering, where we just find the nearest neighbor, nearest centroid in the sloppy centroids, with a one-dimensional approximation for neighborhood, was good enough to put a tight bound on the overall clustering quality. Now, I use several more. It doesn't seem to matter much, but it seems nice to be secure about that. And the algorithm is you find the approximately nearest centroid. If it's within a threshold, then you add the current point to that centroid with a stochastic threshold. If it's outside the current threshold, you just assign it to a new centroid. And when the number of centroids gets too many, you recursively cluster the centroids themselves using the same algorithm. And you may increase the threshold so that it becomes more and more likely that the centroids will have data stick to them. And so that the rate at which you have to recursively cluster becomes less and less common as the threshold grows. And so the resulting surrogate is a large number of centroids. Yeah?
You said one thing you do there is to cluster the centroids together.
Yeah.
At some point. Doesn't that mean that you have to increase the neighborhood that you're using?
No, because the centroids may have drifted around, and so they may have wandered actually fairly close to each other. And that is the original paper said always increase the threshold by a factor of something like 1.5. And that was in order to gain a guaranteed time for convergence using very simple bounds. But I found that in practice, it is not uncommon for the centroids to collapse reasonably well, especially early in the algorithm, and keeping that threshold small gave a higher quality cluster in practice. And so what happens is if I don't see a good size collapse, like 2 to 1, then I increase the threshold for the next time around. If I do see a good collapse, clearly I didn't need to. And then I don't. So that's a slight refinement we've added in our implementation, is to optionally increase the threshold and make the cluster stickier. But in any case, we get a large number of centroids, and we can either cluster those recursively, or not recursively, cluster those with a high quality clustering algorithm to get a small number of centroids, or we can use them as is, because they describe the distribution of the data already with reasonably, provably good fidelity. So we don't actually need to cluster, in all cases, down to a small number of clusters. We could use the surrogate directly for some other algorithm, like feature extraction or just any sort of thing. Either way, it's very cool. We can get to that surrogate very quickly and use it however we'd like. So, the key step in here is how do we find the nearest centroid? How do we find it fast? And the first rule, of course, is when optimizing, don't do it. Whatever it is that's expensive, don't do it. Second algorithm is, of course, don't do it, as in convert the expensive operations into smaller, simpler operations. Can we convert a vector floating point multiplication and square root into a bitwise XOR of one quantity with another? And the third rule is, well, we could project to a smaller dimensional space. So here's the first search algorithm that could be used. And that is just project onto that diagonal line the original data. Things that are close together originally will be close together in the projection. And you will have some false positives of things that were far apart that appear to be close together in the projection. And if you project a few different times, you have a very good chance of finding the actually closest thing. And you can even cheat, because the projection defines a total ordering. You can use Java classes like a sorted set to do the search for you, typically in a reasonable amount of time. And even in pretty high dimensions, if you have a number of these, say 100 dimensions or 1,000 dimensions, you have a 90% chance of not finding the closest neighbor, closest centroid, but you have a 10% chance of finding the closest one. So if you repeat that search with different projections several times, you wind up finding something very close to the closest thing. And so this is a way we make it dimensionality independent, is we can just do, say, 10 of these random projections. It now is 10. That is the effective dimensionality of the data. Not 1,000, not 10,000. Whatever it is, it's now 10. And
So are you clustering like in the hell and all this distance kind of?
no. Just random mass projections. Just any direction. And because they are randomly chosen, we get these probabilistic bounds on how likely it is that we find the nearest cluster, or at the very least, we assign it to a cluster that is about as close as the nearest cluster. That bound is good enough to say that the surrogate is good enough to give us a good clustering in the end. So good enough is good enough is the rule going on here. Yeah.
So with random, are you just using pseudo-random number generators? So it's just a sequence that does not repeat for a certain.
So yeah, we just pick pseudo-random numbers. We just use dev urandom, which uses the entropy pool in the machine to seed a random number generator. And I don't even much care if it repeats. We would like it not to have gross, horrible linear congruential behavior. But all reasonable production random number generators are very nice in that regard.
They don't repeat, usually it's a sequence number that doesn't repeat for a while.
The total sequence doesn't repeat. Individual values or sequences could repeat, but it doesn't much matter, as long as it's incoherent relative to the original data.
Is it, do you have a way, if you reduce the dimension, to map, like, to map back to non-vector size data?
Well, that's what the one-dimensional projection does. It projects to a total ordering.
Like, you want to go back and you want to see, like, does this make sense?
Oh, yes, the hard question. Doesn't make sense. I'm sorry, we're talking mathematics. That's different. We're talking about, is it a good
I mean, is it
cluster?
kind of like sometimes you keep like your vector and you keep the actual data, like as a tuple?
So we always keep the original data, of course, to try to find out what the true distances are, because we need that original data in order to complete the average for the centroids, so that we can later do the proper clustering in memory of the centroid surrogates. So we always keep the original data in that sense. Here's a second acceleration method. What we can do is we can do mini random projections of the data. And if the vector is on average kind of collinear with the projection, we record a 1. If it's anti-collinear, meaning pointing the opposite direction to some degree, we record a 0. We do this 32 or 64 times, and we get a 32 or 64-bit number. Now, if I define a projection in a half plane that way, things that are pointing the same direction and are near each other kind of have a high probability of being in that same half space. Because it's only if they were just right on the edge that they would be on opposite sides. And if I have many half planes, like this one, and this one, and this one, on average, the number of times they have the same sense, 0 or 1, would be rather large if they point the same direction. Now, we want a distance. And when we say point the same direction, we're talking about a dot product. But distance and dot product are closely related here, especially if these are unit vectors. And so we can estimate this cosine theta, which is the key term in this distance, using this XOR. And here's how well we can do it with 32 bits. 32 bits? 64 bits, excuse me. The illegible horizontal axis goes from 0 to 64. So if the XOR has very few bits that are non-zero after we XOR those, then the two representations were nearly identical. And that means the cosine of theta is near 1. Now, very few of these randomly chosen data points have that characteristic, but that's okay. And likewise, if we have an XOR of 64, these are nearly exactly in the -1 cosine sort of direction, meaning 180 degrees apart. And if they have 24 to 38, 40 bits in the XOR, they're kind of at right angles, and that's where most of the data is. So this provides a nice approximate value for that, and here's how much speed up we get. The speed up is the horizontal axis. This is with 32 bits, and going out here to 30x speed up with no cutoff. This is an adaptive cutoff. We get good speed up, and with 64 bits, we get even more speed up. So we can find the nearest cluster two different ways now. And we can even do a brute force search, but we want to avoid the brute force search. We want these accelerated searches to avoid the actual kappa appearing in our cost. We want log of kappa or better. So that's what we're going to do. So internally, what we built were things on the Mahout math package that allowed us to delegate to interesting new kinds of vectors. Weighted vectors, centroids, LSH vectors that we could XOR, things like that. We also defined a searcher interface which defines searching through an in-memory set of vectors, and the clustering classes themselves. Here's how the algorithm performs in terms of speed up and in terms of gross cost. So with a single thread, it takes 200 microseconds per data point in 10 dimensions to cluster this data, doing the fast surrogate. And you can see that this gray line is the perfect speed up as we add the number of cores, and at around 10 to 12 cores, we begin to deviate, probably because we're running into the garbage collector. The garbage collector is sitting there working in the background as we make garbage and do computing, and at about 12 threads, we start running into it. And this is a 16-core machine, so there's a few threads doing parallel garbage collection, but we've got essentially perfect speed up down to there, and our best speed is, on this log scale, 20 microseconds per data point, or 20 seconds per million data points. And as expected, this is many orders of magnitude faster than the k-means that's already in Mahout. It's much faster, yeah.
You vectorize
Vectorize. Vectorize
this.
is
Like
what's in.
use the SSE
I don't much care whether or not this gets to use its SSE instructions or not, and that's because this is probably I/O bound
to. Okay.
at this rate. To read a data vector, just a set of predictor variables, to convert to floating point in some representation, to get down to 10 dimensions, probably costs me a very large fraction of 20 microseconds on average anyway. And so whether I use the vectorized arithmetic in there or not, I'm not sure it much matters. The place where I think I'm wrong on that is here, because what I'm doing is I'm doing a dot product against 64 vectors of that, and so that should turn into a very efficient numerical kernel. So that's the one place where I think this would work well. So anyway, we have linear speed up essentially there. And since this graph was made, we've actually implemented a MapReduce version. And if you think about it, if I divide the data into pieces, and I come up with a nice probability distribution for each piece, and it's of the form of weighted samples, I can just take the union of those two sets of weighted samples. I have a new set of weighted samples that's a description of the distribution of the union of those two data segments. That means I can build a MapReduce program where the mappers all do this surrogate algorithm, and the reducer just kind of glues them together and clusters them all. Doesn't have to do anything clever at all until there's a gazillion mappers, in which case it does one step of this surrogate and Shazam, it's done. So the MapReduce is nearly trivial. It does the same algorithm with as many threads as I care to on every mapper, glues them together, and does the surrogate the clustering of the surrogate in memory. And the threaded version shows linear speed up, and the MapReduce version shows essentially perfect linear speed up. So that means that the 20 microseconds, the 20 seconds per million data points, can easily extend to 20 seconds if we had no MapReduce overhead per billion data points, which is by far the fastest clustering I've seen in practice. And we'll prove that shortly. So anyway, how well does it work? There's theoretical guarantees. The original paper provided those. But if you evaluate on synthetic data, you find it with very high probability gives you exactly the correct clustering that you want. If you evaluate on real data, we cluster the classic 20 news groups data, which is small enough that we could do a ball k-means on the original data. These surrogate plus ball k-means gave us slightly lower error than traditional k-means and virtually identical error to the ball k-means. So the surrogate method works in practice and in theory indistinguishably from doing the full clustering. And we now can do things like one of our customers has 100 million credit card customers. They'd like to cluster those so they can do k-nearest neighbor search really fast. And things like this allow k-nearest neighbor modeling to proceed at about literally 1 million times faster than their initial prototype. That's a big deal. Any 3 orders of magnitude is a big deal, and 3 orders of magnitude twice is a really big deal. And the reason that that works is that if you have data points and you want to find the nearest neighbors, then just clustering and then Voronoi tessellation gives you a nice approximation of the nearest neighbor search. So, the nearest neighbor stuff seems to work. Nearest neighbor algorithms can be blazingly fast if we have blazingly fast clustering. I can't say that. And blazingly fast clustering is useful in its own right. It's useful for vector quantization, it's useful for machine learning, it's useful for all kinds of things. And it is now fast enough to be competitive with disk I/O, even on conventional hardware. And that's kind of exciting. So that's the talk. That's the results, that's the theory. We're hiring, I think I mentioned that. You can get in touch with me, you can get the slides. The code is open source, it's in Mahout mostly now. It will be entirely in Mahout in the 0.8 release, which should be coming up in a month or two. And you can get a hold of me any way you like, even right now. So.
In person?
In person. Oh, yeah, I can prove it. Watch this. See, look at that. Sorry, upside down. So, any other questions? We had a lot of good questions along the way. Yeah.
Just a small question, as in addition to this information, if people are interested in more news on Mahout, there is now a Twitter entity for Mahout, which is @Apache Mahout written all together.
She is the Apache Mahout Twittermeister. And so, okay, there you go. @Apache Mahout written all together. There we go. Correct. The last line there. You can follow that if you want news about Mahout. That includes bug fixes, that includes releases, general news. And Mahout's kind of cool. Mahout does really good recommendations. It has a nice linear algebra package built in, and it now has super fast clustering. So, come on in. Yeah.
On these tests, were you using your own MapR replacement for HDFS?
I have to put the hat back on to answer this question. The man asked if I was using MapR for the tests. Of course. Why would I use anything else? The reason we did that is A, we had training clusters laying around, but B, also, the invocation overheads are very low in the MapR cluster, and so you get better measurements of how long things actually take in the theoretical optimum. And in general, Hadoop-based MapReduce has a lot of overhead, but as was shown in the minute sort and the terasort records that MapR set, we've knocked that overhead down substantially, especially for large clusters. But these were set on relatively small clusters of up to 10 or so nodes so far. But we see perfect speed up as it is, and we see perfect speed up even across thousands of mappers on small clusters, because everything's independent, you can just add up the times to see how it does scale. Yeah.
Is there any guidance about the number of clusters you're generating? Like, if you're just going to do 10 clusters, it doesn't matter if you have 10 to the 9th or 10 to the 15th records, just sample down to 10 to the 5th and do a clustering on that. That could be a reasonable sample, could be just as good as something fancier. So, I mean, I imagine if you get up to 1,000 clusters or some large number where you look at the ratio of the number of records per cluster.
Greg makes the point that if you have a small number of clusters, that a small amount of data suffices to get a very coarse view of the distribution of the data. And if clusters are a surrogate for the data distribution, it's true that a small amount of data gives you a low resolution view of the data. But if you take kind of a non-parametric look at the world, the more data that you have, the more resolution that you can hone in on the distribution of that data. And so it makes sense to have more and more clusters as you get more and more data. And in fact, by that standard theorem, about log of the number of data points is a fairly reasonable number of clusters. For most data sets that we have, 1,000 to 10,000 clusters seems quite justified if you have lots of data points. This is in contradiction to old style clustering, where the goal of the clustering was human interpretation, where you would do clustering on behavior and you would say, those are yuppies. You know, these are urban professionals and things like that. There, what you wanted is a small number of clusters because you had to go through by hand and try to interpret those for your customers. But here we're looking more at automated consumption of these clusterings. And as such, we don't really care if it's interpretable. We care if it describes the data well. And with lots of data, you can have more clusters and get better results on held out data. And so I think you should. But if you want a small number, yes, you can downsample. Now downsampling costs time as well. About as long as it takes to do this clustering. You pick which one you want to do. Do you want to downsample or do you want to just do clustering? Because you have to look through everything to downsample. This is a downsampling. Yeah, in the back. Straight.
Is there any place this particular code is implemented and which we like a public can access it to load some sample data and run it with
As the man next to you is saying, it's part of the Mahout in the trunk version.
I know it's
Apache
the
Mahout.
code is there.
Yes.
The whole setup is done that you need is MapR with this and then running.
The benchmark.
Right. Is that setup available publicly?
The data set that we used for the test clustering,
No, the Hadoop with the
there is no Hadoop, well, MapR gives out Hadoop with Mahout. The version that we distribute is 0.7 at this time. We don't distribute 0.8. 0.8 is available on GitHub or from Apache. It's very easy to compile and use.
So if I have to go and find, I have to start from the track.
Yeah, right now you do.
I'm hoping somewhere it is available, then I only need to get my sample data and run it and see.
I'll take that as feedback and try to make it easy.
Thank you.
And in fact, Sri has been active lately on the drill mailing list. And there's a connection here because these operators could easily be integrated into Drill, Apache Drill, whose goal is to do full table scan sort of data processing, nominally in a SQL environment. But all of these operators could be integrated into Drill to do clustering and k-means join instead of SQL condition logical join. So that's kind of an exciting capability here as well. But yeah, I'll keep that in mind, Sri. It's quite plausible to build an EC2 AMI with this already built in. That would be pretty easy to do. Yeah, may well do that. And certainly, as we go forward, as we establish more speed sort of values, having those replicatable easily is important. So yeah, that's an important thing. There was another question, yeah.
Have you done anything or estimating adaptation versus if you have new data coming in, recomputing the whole thing?
Yeah, so the man asks about adaptation to new data, and presumably new data where things haven't changed.
Right, and it might also be some unsupervised. You might not know, you might have to make estimates of what the value of that new data is.
Well, this is by nature unsupervised, so already. And the key question
is...
is...
Things like fraud, obviously, that is a
Yeah.
supervised piece. That's an indication.
Yeah, but there could be unsupervised parts of supervised learning problems. Now, the question is, when does the world change? Well, we know it changes pretty much all the time. So, especially in adversarial settings like fraud, when have they learned enough new tricks, that my old counter tricks, spy versus spy, no longer apply. And that is, in general, a hard problem, because as much as we try to learn more elaborate models, we also then make the assumption that the world is not changing, and we preclude that detection. Now, the one thing that is available in clustering is this average distance to the nearest neighbor. And if that sits there and goes bubbly, 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 the low value suddenly changes, and we can use a change point detector of any sort because it's a one-dimensional problem, then we have evidence that things have changed. But more interestingly, this is an online algorithm. Online, literally online. Meaning I could build a real-time clustering that you could probe at any time and would give you a nearly optimal clustering of all of history, or less than all of history. The weights on the surrogate could decay over time. And so I could give you multiple clusterings. This is the recent clustering, this is the medium, middle-aged clustering, this is the old and wise, but possibly very misinformed clustering. And then we can do real-time learning on top of those to try to decide, should I give you the young one or the aged one? Is it like fine wine, or, is it gone, just, is it out of fashion? And so you can actually do that online now with these algorithms. So that there's some very, very exciting possibilities there that were just not there before. Yeah.
So are you streaming or running mini batches or batches? What's your batch interval when you say online?
When I mean online, I mean online. You get a new clustering every sample if you want it. So what happens in the online method is a new data point comes in, and it is applied, and you get a new surrogate set.
Is there a window where you're...
No, there's no windowing. It is...
Does it blow up on you eventually? Or?
The number of surrogate data points increases with k log n.
I mean, how it's online, a lot of people use a window.
A lot of people pretend online means, well, I'll get more data, more memory later. But that isn't really online. This really subject to the k log n. So if you have a few megabytes of RAM, it will last as long as you can feed it data. A few hundred megabytes of RAM. And so it's a unit-sized update to a very slowly growing data structure. And at any time you want, you can derive from that data structure a clustering of all of the data you see. That's what I mean by
How are
that.
you streaming in your test?
You can stream in many different ways. One way is to stream it all through one machine. And if you get one data point spaced out more than 20 microseconds apart,
Are you
that's
using
okay.
like a proprietary, using like 0.2 or 0.2 or are you using
I am not doing this right now.
Oh,
If I were to do this, I would use Storm, which uses the LMAX disruptor framework internally for streaming, and is pretty efficient at that level. I would still pay a serialization cost, which would be several microseconds per data point. But we would be able to achieve essentially that speed.
What do you do about the guarantee of one or more, like if you have a failure? In Storm.
So the question is, how do we deal with failure?
Yeah.
And in common with any online system, there are two ways to deal with failure. One is hot, and the other is checkpointing. And in Storm, checkpointing is the easier one. So you checkpoint periodically, and you do not acknowledge tuples until you checkpoint again. And so you will have disk I/O proportional to the number of data, to your data rate, but linearly dependent on that subject to the log rate. And you will have to replay any data points that arrived after the last checkpoint, which you will get again on a failure. So that's an easy way to do it. You can do hot as well, and plus checkpointing, and you get faster recovery that way. That would use the global transmission of storage. But either way, you can really do online anytime you want it. You can get a high quality clustering of data, literally online.
Do you let it do you let it see check?
This is all thought experiments, and so how I do it.
So you haven't done it yet? but you say you've thought about it and you can.
And the MapReduce results. So, yeah.
What are the conditions that you might be able to just use the trivial projections of just a single dimension along an axis? It would seem like that would reduce the whole dimension multiplication.
Yes, it makes it faster to do that by the proportional to the number of projections. And so the question was, when can you use one? And the paper, the Meyerson, Vining and Shipton paper, I put it in the authors because I can't remember what the original one was. That proved for the case of a single projection and for the case of well-clusterable data, a bound on how good the clustering would be. And with high probability, it's a very high quality clustering, comparable to the effect of just clustering with bulk means the entire data set. Now, in practice, you don't have theoretically well-clusterable data. So I think it's prudent to do more than one projection. But I haven't seen much difference either. 1, 4, 10, 40 projections doesn't seem to be much difference. In the microcosm, as you trace the code, you see some difference. In the final average squared distance, you don't see much difference. So, de gustibus, your taste may change. Your mileage will vary. Any more questions now that we're in the dark? I think you guys are leaning on the dark light switches there in the red jacket. Are there light switches right next to you? No? Okay. Perhaps not. So, more questions? I thought I saw. Thank you. It's just a thing. Maybe they have time.
You must not be hot water.
Yeah. Yeah.
Could you give them concrete example applications that MapR use? Like when you get the result, you have more clusters than how compared to other clustering algorithms, how do you use the result?
Well, I can give an example of how I've used k-means clustering and data mining in the past. And that was an insurance problem. We had lots of symbolic inputs. Symbolic like zip code or zip 3. Symbolic like this kind of car. That year of the car. We also had symbolic inputs like a history of traffic violations. It's variable length. You get a special symbol, say every year, just to indicate the passage of time, and you have various other symbols. And the other symbols may have different conventions even. They may not even be a close. All difficult inputs to use. The easy ones are all numerical. And so you can say, when was the last insurance loss? How long ago? Those sorts of things. What's the average income of the person? But all of these text-like or symbolic categorical data were lost to most of the modeling. So what we did is we took two objective outputs. One is attrition, one is loss. And we found symbols that were overrepresented in one side or the other of these two objective things. That gave us symbolic sets, and they gave us positive and negative scores according to just IDF weighting on 64 dimensions of symbolic data. We now have 64 times 2 dimensions of numerical data. And at that point, the learning algorithm, which was a backpropagation sort of thing, could not learn a useful model. It would explain 3% of the variance on held out data. Just no value whatsoever. But when we clustered the data using our old dark ages type techniques, not these modern techniques, when we clustered the data and used which cluster and what the distances to the clusters were, the model was able to explain over 70% of the variance and was the highest performing model that the customer had ever seen on that data. And so we have here a couple of steps. Transformation, objective outputs, multiple targets in a process called LUD1 algorithm. Second step is k-means clustering, and the third step is learning against cluster proximity features. Now, only the combination of all three in that order produced the high value. learning on the Lublin features did not help. Although Lublin features after clustering, after cluster proximity features, that we got the high quality model scores. So there's a practical example of this. Yeah. Yeah.
How does changing dimensions stay outside affect the way the clustering is going to work in general?
The man asks if I scale the dimensions or rotate them, what happens?
Yeah, like 0.5 and
K-means is well known to be very sensitive to the metric. And by scaling the axes, you're changing the metric. And so if I have 4 clusters that are at the edges of the square, press this dimension and extend this one, I basically have 2 clusters at that point. That I have more than 2 clusters at that rate. And if I stretch it the other way, I have 2 different clusters. And so K-means is not invariant to linear scaling transformations. It is invariant to rotational, but not scaling, but not anisotropic scaling. So just know not to worry. But this is true of a lot of metric-based algorithms. Screwing with the metric screws up metric-based algorithms. And they don't apologize, they just say it's your fault. And good choice of that. Knowing your data, choosing your variables well, scaling them well is extraordinarily